Hello students, welcome back. Let's go to section 2 of this notebook, Constructing First-Order Linear Systems. What is this all about? In section 1, we studied the theory of systems of first-order linear ODEs. And then, after this, in sections 3, 4, and 5, we are going to learn how to solve the first-order system. Now, what about higher order? Basically, that's what we are up to right now. And this is a roadmap. We're going to learn how to reduce arbitrary order system down to first order system. That's the purpose of section 2. Once that's done, we can solve the first order system using all those techniques from sections 3, 4, and 5. Okay, let's begin, and we have to start somewhere, so let's begin from the simplest case. If we have just one equation from one linear ODE of arbitrary order, let us study how to bring it down to a system of first-order differential equations. So let's start from here, and then please note that the leading coefficient cannot be constantly equal to 0 because this is order n. If this is constantly 0, then this part will just drop out, and this is no longer order n. So we can divide by Bn. So that's what we do, divide by Bn, and then flip all these to the other side, and we have the standard form. We can solve for yn, or the nth derivative of y, like this. Now this is a little bit inconvenient with all those fractions, so let's rename all those coefficients. Name this one as a0, and then this one as a1, and so on and so forth. This one is an minus 1, like this. And finally, this, we name it as f. And we have the standard form. So it's just standard process from here, general form, to standard form. We can always do that because leading coefficient cannot be always 0. Okay, the first manipulation is done, and that's rather trivial, just warming up. Now here is the ingenious step, and we take this substitution. x0 is y, the zeroth derivative. x1 is y prime, the first derivative. x2 is y double prime, the second derivative, and so on and so forth. And xn minus 1 is n minus first derivative. Do you see this? Now, under this substitution, we got n functions, x0 to xn minus 1, and we are about to form a system of first-order linear differential equations associated to x0 to xn minus 1, and here's the system. x0 is equal to y, so if I take the derivative, so x0 is equal to y, so if I take the derivative, that's y prime. But then again, that's x1, so that's how we get the first line. Doesn't make sense. x0 is y, take the derivative, then we get y prime, and that's x1. Now start from x1, which is y prime, take the derivative, then we have second derivative. And second derivative is x2. And then we start from x2, take the derivative, then that's going to be the third derivative, that's x3. And that'll continue. And that's not going to continue all the way to infinity because at some point it'll have to stop. And from xn minus 1, if you take one more derivative, then we have nth derivative, and this equation applies. So xn minus 1 prime is the nth derivative because we took just one more derivative. So we have to write this one in terms of x0, x1, x2, and so on. So y is equal to x0, y prime is x1, and so on. So we have this. So the conclusion? Through this substitution, we ended up with a system of n first-order linear ODEs like this. So arbitrary linear ODE with order n transform into the first-order system of linear ODE. By the way, the matrix expression becomes like this, and This matrix is rather special matrix. It is called a rational form. And let's see. It's not going to be easy to deal with this kind of thing in linear algebra, Math 3330. So it'll have to be some kind of 4000 level course. And there we're going to deal with some rational form. And rational form of a matrix, a square matrix, looks like this. Either all ones right above the diagonal, and then some non-zero numbers only on the last row, or it's transpose, all ones right below the principal diagonal, and then non-zero entries only on the last column. This kind of thing is called a rational form, and this is an important class of matrices. And of course, one of the motivation why that is so important is related to this. As a matter of fact, it's useful in differential equations, so it's useful in linear algebra as well. In any case, this is actually well-studied matrices, so we can go ahead with all kind of theories of linear algebra and matrices to study this and answer the question about these differential equations. In the end, we ended up with this kind of one-line expression, naming A as this matrix here, and capital X is my vector function. Capital F is the vector function given by the non-homogeneous part. Here, I'm using this arrow to denote those column vectors, but many times I'm not going to bother with these arrows because column vectors are matrices too, n by 1 matrices, so I can use this capitals for matrices and just get away with it. So very frequently, actually most of the time, I'm not going to bother with these arrows, but here I decided to use those just to avoid confusion. Okay, so much for theory, and let's go to an example problem. Let's keep it simple. Just second order ODE, and it's a linear ODE, so we can bring it down to a system of first order linear ODEs. It's second order, so we expect two equations, and let's see how we do that. So we can start from x0, but I decided to start from x1 this time. So x1 is y, x2 is y prime, and then if we had third order, then I'm going to need x3, but no, stops here. And then let's find out the system. So x1 prime, what is x1 prime? It's y prime, isn't it? x1 is equal to y, so y prime, and that's equal to x2, just by definition. Make sense? Okay, how about x2? Derivative x2 prime, and that's y double prime. Yeah, x2 is already y prime, so take the derivative again, that's second derivative. And what is second derivative from this ODE? I have to solve for this, so looks like I'll have to flip these to the other side. So it's gonna be minus y minus ty prime plus sine of t. Did I do this right? So therefore this is minus of what is y? x1 minus t times what is y prime? That's x2 plus sine of t. Looks like we have the system. x1 prime, x2 prime. So we can write like this. And that is equal to, and that is equal to, and this one, oops. Let's put some space in between, just for aesthetics. Oh, wait a minute. I made a mistake. That should come down here. You see, this is second thing. And this is the first line. Sorry about that. That should be x2. Okay, all right. Now that looks better. So we got the desired system of linear ODEs, the first order system of linear ODEs, because we don't have any second derivatives at all. Oh, we have an initial condition here as well. Y of 0 is 1, y prime of 0 is 2. So, okay, all right. So initial condition, y of 0, so x1 of 0, y prime of 0, so x2 of 0, and that's equal to 1, and that's equal to... All right, is it complete? That wasn't too bad, wasn't it? The initial condition, that's always easy. Y is x1, as we defined here in substitution, and y prime is x2. So here, we have first line, second line, that's always easy. And then as for the system, well, x1 prime is x2, okay, by design. x2 prime, which is y double prime, in that case we have to go back to your original linear ODE. In my answer key here, I use a matrix expression like this and that, or with capital like this. They will equivalent. Okay, we just went through an example of reducing one linear ODE of arbitrary order down to a system of first order differential equations. As a matter of fact, if we have order n, then we need n equations, n first order linear ODEs. Now, what if we start from a system to begin with? Now, this is going to be an optional topic because we have some really tedious computation, and I hardly doubt if I'll ever write this kind of problem in the exam or even homework, but for the sake of completeness, let's discuss this as quickly as possible. So let's begin with a system, and I mean, we may have some arbitrary the orders for each line, and we have m functions to deal with, y1 through ym, and then they have some arbitrary order for each equation, but we can always select the maximal order. For example, here's an example. I just created this as an example, a concrete example. And then y1 has order 2. In first equation, it goes up to second derivative. But in second equation, it goes only up to the first derivative. And it goes to second derivative again. The maximum is second derivative, so the order is 2. How about this green function y2? First equation goes up to third derivative. Second equation also goes up to third derivative. But third equation, it goes only up to the first derivative. But still, the maximum is 3, so order is 3. And here, because of that, the coefficient is 0. So basically this one and also that part actually disappear. I use all those 0 to denote that, theoretically you can push everything up to the maximal. Same thing goes here. So in this kind of circumstance, we can algebraically solve for y1 to the maximal derivative, y2 maximal derivative, ym maximal derivative. Because there are m such unknowns, you can algebraically solve it using the elimination and substitution method, just algebraic method, and you're going to get some expression, and so on like that. Just an algebra. For example, in this example, you can algebraically solve them, you're going to get something. Exactly what those are, that's going to be rather tedious computation. And down below somewhere, I use Mathematica commands to actually get those done, but I don't think that's really important. Anyway, the idea is you can solve for these derivatives And then you take these substitutions. So x11, y1, and then x12, first derivative, x13, second derivative, and so on and so forth. And y1 is complete. Next, y2 prime, y2 double prime, until that's completed, until everything is done. And I can put all those together as a system like this. So up to here, they're all about y1. And then up to here, they're all about y2, and so on and so forth. And then this is about ym. And then consequently, we have some matrix expression. But what is this matrix A? That's going to be really complicated, so I wouldn't really bother. In any case, it is possible. So any system can be brought down to a system of first-order linear ODE. So if you can solve a system of first-order linear ODEs, then theoretically, at least, we are through. As for actually bringing all those complicated systems of arbitrary order linear ODEs down to the first order, that's just a tedious computation, tedious algebraic computation, which may be too tedious for humans, but for computers, no big deal, as a matter of fact. Do I have enough time to demonstrate something here? Okay, the original system here. Yeah, example I just created. And then express it in the standard form. Okay, so solve for y1, y2, y3, all those final derivatives. And then I just use mathematical commands. You see, this kind of commands to get these expressions done. But in any case, they are possible. So we have all those y expressions up here plus non-homogeneous, or the y expression, non-homogeneous, same thing there. And then you can use those substitution, x11, x12, and so on, to get the system of first-order linear equations. Goes up to 6 because order 2 plus 3 plus 1 goes up to 6. And then first two about y1. And then these three are about y2 because that one has order 3. And the last one is about y3. That one has order 1. So there you go. But you don't really have to worry too much about these kind of computations. Whether it is possible or not is a problem, and then we proved it, and that's sufficient. So what did you just accomplish? No matter what system of linear ODEs we have, we can always bring it down to a system of first-order linear ODEs. Always. So if we can solve first-order linear ODEs, then we are through. How do we do it? Well, all right, we have section 3, 4, and 5 for that reason, and also entire lesson 15 for that reason.